long. You don't have to type stuff in. You can run it from there. Some of it takes a little bit longer than other parts, so you're welcome to run it at home or whatever in that. But basically, we're talking about power through simulation, the idea of the power study here. And kind of the motivation is that often we'll start with a power study where the two most common questions are either how big of a sample do I need, or what are my chances of a successful study? And so those are the two kind of questions about what is a power study. There are other questions that probably should be asked more often that you can do with a power study when done well. So, what does no effect look like? So if your null hypothesis really were true, and I know some people argue that no null hypotheses are ever true, to which my response is my null hypothesis is that nobody will give me $10 million within the next week. Feel free to prove that false. But sometimes it's interesting. Okay, if the null hypothesis is true, even if you don't believe that would ever happen in the real world, what do things look like then? And so what might happen? If my null hypothesis might not be exactly true, but it's equivalent or close enough, what would things look like so that I can see, okay, I can still get, if I'm doing multiple comparisons, how often am I going to see something that's not really there, things like that. What does low power look like? Okay, if I'm doing a study with low power, what are likely results for some of those types of cases? Think about what are the real rates under different circumstances. There's the traditional type 1 and type 2 errors, but some people are talking more, mostly I get this from Andrew Gelman, but type S and type M errors is better than type 1 and type 2 errors. Type S is a sign error, basically saying that the true effect is negative and I say it's positive, or the true effect is positive and I say it's negative. A type M error is a magnitude error. So the effect is really small, but I say it's big. That's a type M error. Or it is really big, and I say, well, I don't think it's very big, and I can't distinguish it from 0. Those would be the type M errors, and sometimes those might be of more interest there. And so you can look at how often those types of things occur when you're simulating as part of a power study. Okay. We can also look at things like robustness to our assumptions and their effect on the power as well. So kind of the traditional power study, you go in, you say, well, I'm going to assume everything's perfectly normally distributed. I'm going to work out my power accordingly, and I'm going to run my study. But what if what if everything's not perfectly normally distributed? If I've got a big enough sample size, I can use the central limit theorem, and I can still have a correctly sized study. But how much is that non-normality affecting my power? And in some cases, it might not affect it very much. In other cases, it might affect it quite a bit. And if you don't learn that up front, it can cause problems a little bit later on. Okay. How are people trained to do power analyses? Now, your experience may differ. It's been over 30 years since I took my first intro stats class, which makes me feel old now. But we didn't have these fancy computers on everybody's desk, and that I think we had one assignment where we went into a dumb terminal lab tied to the VAX computer that had its own big room down the hall, and ran a early version of the S language, for one assignment to make a histogram or something like that. But most of what I've seen in kind of an undergraduate curriculum in that is most power studies focus on the simple cases. One sample z-test with a known variance, or a one sample test of proportions. Those are simple, straightforward. You can do all the math. You can show it and say, look, here's power. As you change the mean, this is what happens. As the standard deviation or the sample size changes, this is what happens with power. Okay. For these simple cases, there are a lot of pre-built tools that work nicely. There's functions built into R. There's functions built into probably every decent stats package out there to do these simple cases. Okay. My problem with the pre-built tools, though, now, if I'm doing a simple t-test, I will use power.p.test in R, okay? Sometimes I'll do some of this other stuff as well, but I'm saying not to use them. But I found that most of the pre-built tools really focus on simple problems. And a lot of the stuff I have to do is not simple problems, okay? So sometimes I do simple problems, that's great. but as problems become non-simple, the pre-built tools don't do as well. So I've seen different rules of thumb. Okay, you're doing a multiple regression. Well, if you treat it like a a simple t-test on the slope you're interested in, and then add an extra 10 patients per additional covariate, that gets you in the ballpark. It's like, okay, so that's a rule of thumb, and some rules of thumbs work better than others. Okay. The other thing I don't like is things get a little bit more complicated. Often the effect size becomes complex or confusing. So there are power functions and packages for R that says, okay, you want to do an ANOVA with more than 2 groups. Okay, plug in your effect size. And this effect size is in terms of a non-central F distribution. And I want to think of, well, okay, what if the mean of group 1 is this, the mean of group 2 is this, and the mean of group 3 is this? That I know how to simulate, but translating that into an effect size that's a scaled non-central F thing makes me think, and thinking hurts. There's in the R4 package, there's something about thinking hurts and memory's cheap or something. So that's great. If you're not familiar with the Fortunes package, it's a great package. That's actually what it says. One of my claim to fame is I've got a couple of quotes in there on that too. Oh, I forgot to mention, today is the opening of the Winter Olympics. So, this is probably the second best thing you'll be doing today. But at least you can go home and tell your family that to celebrate the opening of the Winter Olympics, you went to a meeting with over 6 feet of snow in the room. So. Okay. The other problem with these pre-built tools is a lot of times they're hidden assumptions. As things get more complex, there's a lot of complexities. Some of these pre-built tools try to simplify things for you, but because of that, there are these hidden assumptions. Okay? I had one of my coworkers come to me one time. He was trying to do a power study for a mixed effects model analysis that he was going to be doing, and he found 2 different tools that were supposed to give him sample size estimation. He plugged in what he thought was the same information to both of them, and he got 2 very drastically different numbers out as to what sample size he needed. And he couldn't figure out what he had done wrong. And I looked at it, and I ran my simulation in R, and I got numbers that were not exactly the same, but similar to one of them. And the best I could figure out is that the 2 different numbers were based on different assumptions that you weren't able to set. Okay? And so kind of along with that is a lot of the pre-built tools I don't think are flexible enough. Because if they were flexible enough, it would be a whole programming language itself. For more complex problems, you can't make something that's completely flexible without doing some programming. So that's why I think we should get into programming. Okay. So what is needed for power? Okay, if you've never done a power study before or that, when I meet with clients, these are kind of the things I go through. So if I'm going to calculate power, then I need to know what sample size we're planning to use. Sometimes we're starting off, well, this is the biggest sample I can get. We're limited by money or time or something. And so this is the sample size we're going to use. What's my power? So we need to know what the sample size is. Is it going to be balanced or unbalanced? Am I going to have, if it's 2 groups, am I going to have about the same number in each group? Or am I going to have a lot more controls than I have treatments, or vice versa? Is there going to be some type of nesting, hierarchical thing? So how many units within each group, and how many groups am I going to have? I need some measure of variability. Again, if it's nested, I kind of need a couple of different levels of variability. And then I need some type of expected or minimally interesting difference or effect size. Well, how big of an effect or how big of a difference am I looking for? And then any other assumptions depending on what type of study we're going to do. What assumptions go into this? Am I going to have additional covariates? What are they going to look like? Some of those things. Okay. Similarly, other times it comes and says, I want a powerful study. How big of a sample size do we need? So in that case, we need the desired power, the target power that we're shooting for. I have the S there because sometimes it's really, you want to say, well, what sample size would we need for 80% power, 90% power, 95% power, just to see what we can do and what we can afford in that. Again, we need the measures of variability, our expected or minimally interesting difference in effect size, other assumptions like on the previous slide. Okay. Sometimes the hardest thing to come up with there is really what is that difference that we're looking for. And that's one thing I find frustrating sometimes as statisticians. I'm working, right now I work mostly in medicine, so I'll be working with a doctor, and we'll say, it's like, okay, how big of a difference are you looking for? And he says, well, you're the statistician, you should tell me that. It's like, you're the subject expert, you should know something like that. But, we have to talk things through. And the best way I found to look about this and think about the idea of power is using the idea of a confidence interval. And this isn't original to me. I first saw this in a textbook called The Statistical Sleuth. I don't know if they got it from somewhere else or if they originally did it, but that's where I saw it from. And so basically visualizing and thinking about what could happen, I have here, two lines. So this is the line of no effect. So this is a zero slope or no difference between two groups or something like that. And then over here is the minimally interesting effect. That's basically saying if there's a real difference but it's below this level, I don't care. I have the wonder drug that if you pay me $100 a day for this drug and take it for the rest of your life, I guarantee statistically significant that it will extend your life. And it'll extend your life by about 3 to 4 minutes, 30 years, 40, 50 years from now. Okay. Most people are going to say, no way, if I'm going to pay that much for a wonder drug, it has to add years onto my life. Okay. So small effect sizes that we don't care about, you need to kind of say, well, where does this trend? Now, this is going to be subjective. Some people are going to put it different places, but the subject expert kind of has to say, and sometimes I have to start throwing out numbers and say, okay, if this can lower cholesterol by 1 point, is it worth it? Well, 1 point, no. If it lowers it by 20 points, yeah, that's worth it. But about 10 points, and then, I can get narrow in here. So think about where might we end up with a confidence interval? Okay, so if I get this confidence interval here, it doesn't say there's guaranteed no effect, but we're completely within the uninteresting area. Okay, and I'm showing this just one-sided, but you could reflect it over here if you wanted to do it two-sided here. But this is really this is saying I can't say there's an effect, and even if there is an effect, it's uninteresting. Okay, so it's not important enough to do there. Okay, if this were my confidence interval, then I can say, well, it's statistically significantly different from 0, but it's still completely in that uninteresting range. This is my wonder drug that increases life by 3 to 4 minutes if you take it, for the next 20 years at least. Not enough to get excited about. Okay? Here's a confidence interval that now it's clearly statistically significant. It doesn't include the no effect. It does include some of the uninteresting area and some of the interesting area. So with this one, we can say, well, this effect could be interesting, and it's definitely real. Okay, it's statistically different from the no effect. What we'd really hope for is something like this, where it's all in the interesting area. What we really don't want to see is this confidence interval here. Okay, this is the confidence interval that says we just wasted our time and money, because I can't rule out no effect, and I can't rule out an interesting effect. Okay, with this one, I at least know that it's probably not worth pursuing this particular thing anymore, because even if the effect is non-zero, it's very unlikely to be interesting at all. These are kind of successes. This is a somewhat success. This is I just wasted my time because I can't rule out no effect. I can't rule out an interesting effect. So when I talk about power, I like to show a diagram like this. Sometimes I'll draw it out on a whiteboard or piece of paper or something real quick. But just show this and say, so our goal is to get a big enough sample size to make this impossible. And because any of these tell us something, this one tells us nothing. And so we choose the minimally interesting effect so that this confidence interval width is always going to be narrower than this width here. And so that gives us that minimally interesting effect for doing the power. Okay. So some examples of some actual power studies that I've done where I didn't like the existing tools and did simulations here. So these are real cases, and some of these I'll have code for going on here. So, we all know the central limit theorem. I guess I should have added in. I actually have a cross stitch of the central limit theorem hanging on my wall, so, with the Bayes theorem and mean value theorem of integration, so which either proves I'm insane or my wife really does like me, or some combination of both. But it's nerd cred, It's like not very many people have an actual cross stitch of statistical theorems on their wall. So. But my wife lets me program her sewing machine, so it works out nicely. Okay, but we've got the central limit theorem, and the central limit theorem says, well, if the sample size is big enough, but what is big enough? Okay, intro stats classes, they throw out a rule of thumb number like 30, but in some cases 6 is big enough, and in some cases 10,000 isn't big enough. And so 30 isn't a very good place to start there. So this can be good to look and focus and say, well, what effect does the non-normality have on both? Is this going to be a legitimate study? Is my alpha level actually correct? And is how much is that non-normality going to affect my power as well? Okay. Some studies I don't have a big enough, it's all categorical, and so I'm going to use Fisher's exact test. Okay. For categorical data, most of the pre-built tools I've seen are assuming a chi-square test or a normal approximation compared to proportions. But if you're doing a Fisher exact test, now there might be something out there, but I've never found a good tool that will calculate power or sample size for Fisher's exact test. But if I know that's what I'm going to be using, I want to be able to use that in my actual plan here. Okay. This was a real case here where essentially we're measuring a rare event, so it's a proportion, but we're going to have mostly zeros. We're not going to see this very often. So the normal approximation to the binomial is not going to work. So those pre-existing tools don't work. Essentially, the goal is there was some national standard that says, this number needs to be below 4%. So our goal was to show that, have a confidence interval where the upper limit was less than 4%. Now, it turned out that from past information with this particular thing at this particular hospital was around 2%. So we say, okay, if the truth is 2%, like we believe it is, how big of a sample size are we going to need so that that upper limit of that confidence interval is less than 4%, so we can say we're meeting that national guideline or exceeding it. And so to actually analyze this, I used a binomial with the uniform prior, so the beta binomial idea. This was one of my kind of first forays into Bayesianism, but don't tell my Bayesian friends that, I'm actually saying nice things about Bayesian approaches. But it'd be a lot easier to knock Bayesian if it wasn't so useful. Okay. Another thing I run into a lot is kind of these full and reduced regression models, where it's not specifically saying, just a simple linear regression, but it's like, okay, I know that X4 through X8, whatever those are, influence this outcome. But I want to know if after taking those into account, do X1 through X3 contribute to that prediction? That they have some relationship. Now, it's obvious they have some relationship through these other variables, but after accounting for these, do they still contribute or not? And so I'm going to analyze this by fitting a full and reduced model and then doing the ANOVA and comparing and doing that. And, that's a little bit different from just saying, well, is one slope different from zero? I have 3 slopes that I'm testing at the same time, conditioned on other things, and there might be different covariance structures that I want to explore between my different X variables that are going on with that. Okay. Cox proportionate hazards model, another tool that I've never found a good power or sample size tool for. There could be some different ones there. I also often, when you're going, the reason we're using the Cox proportional hazards model is we know that we're going to have some censoring, but we often don't know ahead of time how much censoring there will be. So as part of a power analysis, I can say, well, okay, if we have this much censoring or this much censoring or this much censoring, that's how much it's going to affect us. And we can use that as part of the planning process as well, to say, well, how much follow-up we want to do, that partially limits censoring, and how much do we want to motivate our patients to stay in the study, because that's also going to affect the censoring as well. Okay. Mixed effects models, like I said, my coworker found these 2 different tools for mixed effects models, and they gave completely different answers because of things, some of the assumptions that were going on in them that we had no control over. Okay. Non-inferiority studies, sometimes we do this. So it's kind of basically as your confidence interval is above some equivalence criterion, we're going to be happy. But here we're declaring a non-inferiority successful, even if, kind of a 0 value is reasonable or anything above that. So we're basically saying, well, it's not worse by more than a certain amount. Other things. If you have a multivariate response, I haven't seen any tools for, looking at a Wilks lambda or anything like that. So if you want to do a multivariate response, yeah. So how do we actually do this? So when doing power studies, these are kind of the 4 main steps, the way I think of it here. Is the first thing And I'm going to go through each of these steps on its own slide. So I'll go through here real quickly. But it says, first thing you really want to do is decide what your data is going to look like. Okay, discuss with your subject matter expert, think about how you're going to structure what goes into your data. Then how do we plan to analyze the data? Now that might change, but at least for a power study, you have to have some idea of, well, I'm going to, it might be that I just do a simple t-test, or it could be that I do a full regression to adjust for a bunch of other things, okay? And sometimes I iterate a few times between 1 and 2. I think my data is going to look like this, then I decide I'm going to analyze it this way, and then I realize, well, if I analyze it this way,
put in the standard deviation, I could do that. So then I run the t-test function on x1 and x2, extract the p-value from that. So this function I can run once, get a p-value, make sure that's working. Once I'm ready, I really like the replicate function. It does this great. This says, okay, replicate this 10,000 times, simfun under these conditions. So the same thing that I did with power.t-test. Well, first I'm doing with a diff of 0 to make sure that I get my type 1 error right. But I use the same sample size and standard deviation as before. And then if I take, so out 1 less than or equal to 5 returns trues and falses. So I return a true if it's less than 0.05 or traditional statistical significance, return false otherwise. If you take the mean of a bunch of trues and falses, this is kind of a nice little quick trick, is that gives you the proportion because it turns trues into ones, falses into zeros, and it's the sum divided by the length, and so that's the proportion that were true. And I get out of here 0.0497. Okay, so that's pretty close to 0.05, which is the target. Okay, I can also do a histogram to see that I get something that's fairly uniform. Okay, so under the null hypothesis, a histogram of p-values should be uniform. Okay, and then this is my 0.05 cutoff, just so I can see what that looks like. Okay, so now for power, I'm going to plug in the same thing I did before. So 0.8, I put it in. What's my power? 0.8987. So the internal one was 0.90 something, and so you can see pretty close. My simulations agree with the exact thing. They're not going to match exactly because simulations use random or pseudo-random numbers. You can see my histogram. Almost all of my p-values are less than the 0.05. The few that aren't are still pretty close, so we can see what kind of happens there. If I really want to know how good my estimate is, I can do statistics on my simulated statistics here. So if I use the binom test on the sum of the out2s there, then it tells me that my confidence, 95% confidence interval on my actual power, because essentially I've sampled from a theoretical construct here. So this works nice, and so my power is between 89.2 and 90.45. What the built-in function gave me was close to this one, but it was within this interval, if I'm remembering right. So, you know, those things agree there. And this can be kind of nice. And here, this is a simple case. Well, if this confidence interval is too wide, I just need to run some more simulations, and I'll narrow that interval down. And so if I'm shooting for like 90% power, I'll usually increase the sample size until this lower bound is a little bit above 90%, because then I know I have at least 90% power. Okay. Here's just another quick approach is for simple cases like the t-test. Here, I just generate all of my x1s, all of my x2s, and use x2s, and then use the apply function to go through and do all of that. For simple cases like this is okay. This runs a little bit faster, but here we're talking, you know, a couple seconds to run the slow way on modern fast computers. So as things get more complicated, this way gets a little bit harder. But in case, you know, sometimes I've had people say, well, why don't you just do it this way? It's like, well, in some cases you can't do that. Okay. Well, what does low power look like? Okay. So here's a case where, so I've got a similar function here. I'm just doing a one sample. So I'm generating from a normal with mean diff. I'm going to compare to a null hypothesis of 0. I'm going to run the t-test. I'm going to return the p-value, my estimate, and the confidence interval. And I found a situation here. So if I use a sample size of 50 and a difference of 0.3, it turns out that's about 55% power. Okay, which I would prefer not to run a study at all at 50% power, but sometimes people say, well, hey, it's a coin flip. We at least have a 50% chance of showing something good. What does that do? And people will run this because, well, I can't afford anything more. So we'll run it and see what happens. Okay. So here I'm going to plot the results. So just put in the code so you can see it. Now, if we plot all of our results, we kind of see what we expect. So the vertical lines are the different sample means. The green horizontal lines are the confidence interval for each one. So my truth is 0.3 right here. And you can see I'm nicely randomly scattered around that. Okay, this is kind of an intro stats class thing that I would show to students to say confidence intervals are random. Some of them include the truth, some of them don't. But what if we restrict that plot to only those with a significant p-value. Then it looks like this. And now you start seeing is on the first plot, we had things randomly either side. But if I only look and say, okay, if I run something at 50% power, and I'm lucky enough to be in that 50% that I declare statistical significance, what's going to happen with that? You notice almost always that's a case where the sample mean is too big. Okay, I've got a couple of cases here. When I was preparing this and running this, I did have one case where I had one confidence interval down here. So the type S error was significant in the other direction. But I'm going to get a biased result if I run under low power. Okay, so conditioning on finding. So if I run a low power study, find a significant result, people say, hey, that's great. Even though it was low, I found a significant result. It must really be there. But when you start talking about the estimates here, so here I'm asking, well, how often was my estimated mean higher than the truth of 0.3? Well, that was 89% of the time. So 90% of the time I'm above, 10, 11% I'm below. And that's not really the, well, I'm equally likely to be off either way, okay? I also said, well, how often am I twice as large? Okay, so the true effect size is 0.3. How often am I getting an estimated effect size greater than 0.6? So that was 3.4%. Now, 3.4 might not sound very big, but that's still 3.4% of the time, you know, almost up to that statistical significance that I'm going to claim that my truth is twice as big as what the real effect size is, okay? And with even smaller sample sizes, this would be even more extreme in some ways. I also said here, well, what if, how often was the lower bound of my confidence interval greater than the true value? Okay, so for a 95% two-sided confidence interval, that number should be 2.5%. I should be, you know, too big 2.5% of the time, too small 2.5% of the time, so that I'm correct 95% of the time. 5.6, over double what it should be, that I'm saying I'm significantly higher than what the true value is. Okay, so if I condition on, I say, oh, I'm only going to look at the confidence interval if I get a statistically significant result, my confidence intervals are going to be way too high, way more than they should be. So thinking about what low power might get us, and I think this is more convincing than just saying, you know, we really should get at least 80%, or I really prefer 95% power. If you show something like this and people start saying it's like, you know, if you run a low power study and you get a significant result, it's going to be biased. And people who recognize things like this are going to look and say, oh, I can't trust your confidence interval because you're conditioning on a significant result from a low power study. Okay. I'm almost out of the time where I'm supposed to get questions, but most of the rest of this is just some examples. So you've got this here. So here's a, here's one I did as a mixture of normals. They have the same mean, but different standard deviations. This was something I think was posted to our help where some discussion was going on. I was kind of curious about it myself. So here I'm actually returning the results from the t-test and the Wilcox test, which is, you know, non-parametric here. When I run with the null hypothesis being true, both of them give me about 0.05. So they both work under the null hypothesis. So the mixture of normals here isn't violating that it's a valid test. But these were conditions where if you just did the regular t-test where everything was purely normal, I think this was about 90% power. But with this extra mixture piece going in there, making the tails broader than they were, it actually dropped the power down to about 65% for either of the tests. So 65 for the t-test, 67 for the Wilcox and Mann-Whitney test. So just having you know, some few and not extreme outliers, and then if we increase the standard deviation ratio between the two things, that becomes even more dramatic in what effect it can have on there. Okay, here was my Fisher's exact test code working through here, and so here was checking under the null, and then under a given sample size. But see what I did for here. So this was a 2x3 design, and rather than thinking of, you know, chi-squared non-centrality parameters, how I do my SimFun here is, so under the null hypothesis, I'm saying for each of my three groups, what's the probability of whichever condition I'm interested in. So under the null, I said, well, what if it's 0.5, 0.5, 0.5, so they're all equal. For this particular alternative, I said, well, group 1 is 0.5, group 2 is 0.3, group 3 is 0.7. And I think that's a lot easier than thinking in terms of non-centrality or effect sizes, is you can just take it back to the client and say, if these are your true differences, this is the power that you have. And, you know, that's a scale that's a lot easier for people to understand. Okay. This was the beta binomial where I was trying to show that the true proportion is less than 4%, working on the assumption is 2%. And so for this, with the sample size that we got, so we had, I think our final sample size was higher than 1,000, but we thought we could get 1,000, and that gave us nearly 95% power to accomplish. And so, hey, we can go with that. We can do that. Here's the full and reduced regression model I mentioned I did. So here I use the mass library because it has the MVR norm function where you can give it a variance structure. And so that gives me different correlation structures between the different X variables. And then I fit a full model and a reduced model, and then use the ANOVA function to compare them. And then this grabs the p-value from that to return that. So similar to some of the others. Logistic regression. Here's one where I'm focusing more on the width of the confidence interval than on a p-value. Because sometimes if you're just estimating things, I don't really have a test I'm testing, but I want to say, well, how uncertain am I going to be with the different sample sizes? So you run this at different sample sizes and you say, well, how wide do you want your confidence interval to be? Like, be meaningful there. So there's confidence intervals coming out of that. Cox model. Go through these ones kind of quickly. One idea somebody suggested one time, was kind of an interesting idea, is if you know you're going to be trying a whole bunch of different sample sizes, you can actually build that in here. So here I generate one data set. This is the maximum n. So in this case, it's going to, each data set is going to be 100 large, but then I'm going to analyzing it using it first, the first 10, then the first 20, then the first 30, the first 50. So in one simulation, it spits out for me, say, okay, if I use a sample size of 10, I'm going to have 23% power. Sample size of 20, I'm going to have 40% power, and so forth. It's like I don't have to run it a bunch of different times if I know I'm going to be doing those different sample sizes. So for some things, you know, you might want to build that in. If you've got parallel processing, and one of my L's moved to the wrong place. Shame on it. I thought I ran the spell check on this. Okay, but so ignore the title. Here it's spelled right. But with the parallel library, it's really nice now. Even these laptops often have 4, sometimes 8 cores, so it's not that hard to use that. You do need to sometimes be careful to do like this cluster set random number stream if you want to have something reproducible and have different seeds. If you mistakenly set the seed the same on all of your cores, you don't end up with as many simulations as you thought you did. Is you do the exact same calculation multiple times, but you have full dependence there. So that's luckily there's this, you know, this function here in the parallel package that sets a different seed on each of your things there. I also take my regular simfun and wrap it in this other function because there's not a parallel version of replicate. There is a parallel version of sapply, but it passes, you have to pass a number into it. So I wrap it in this function that basically takes the number that's being passed into it, ignores it, passes all the other parameters onto simfun and runs that. You have to export to your cluster there, but then you can use parsapply to say, so in this case, it's going to run it 1,000 times, split across 4 different cores or 4 different computers. Do that, brings everything together in the end. And again, this was that same sim function for the different sample sizes here, and shows the different results there. Okay. So those are the main things there. And 2 minutes over my 12:50. But I did start triangulating. Okay, questions, answers, comments, throwing vegetables. Finally, somebody actually threw something at me when I made that comment. My life is complete now, Andrew. Thank you. No questions? No answers.
Awesome. I don't see any from YouTube. So
I mean, I've got another thing at 1:30, but I'll stick around till then if people have smart questions. Oh, you know.
So I think this is really cool. I love how deeply you can interrogate the results. And there is definitely kind of a Bayesian flavor to this, right? Where you get a distribution out, you get a whole distribution. But it occurs to me that you could also send distribution in. right? So if your stakeholder or whatever says, we're pretty sure the actual difference is between 3 and 5. Okay, we're going to say we're 2/3 sure that it's between 3 and 5. You could then parameterize that distribution, send it from that on the input side.
Yeah, you can do some things like that. You know, sometimes where we get our effect sizes is, well, this paper, they did a similar study, and for their control group, you know, they found a mean effect of, you know, 3, but there's a standard deviation of 1.2 attached to that. So that's one thing I could do, is instead of just saying use a fixed 3, I could sample from that distribution essentially as a prior and say, okay, if we take that as our truth, I'll sample from that truth and we'll see what happens there. I kind of like doing the mix, as I kind of fall into that real heresy group of still believing in p-values while doing some Bayesian statistics in that. And so both groups hate me because but it's pragmatic. But yeah, so I'll often do a couple different fixed sizes, but you can kind of say, well, with this uncertainty, you know, if we take this, you could certainly do generate your true mean from a prior that's the posterior from another paper, or an estimate from that. Yeah. You could also do, you know, I use mostly normals and binomial type things in my code, but you could easily put in a gamma instead of a normal, just to see, okay, you know, real life things are skewed. Not everything's perfectly normal. I'll use a gamma that has the same mean and standard deviation, and see how does that affect things. Okay, and if it's not very skewed and I have a big sample size, it's not going to affect things very much. But if I'm in a medium level, it can, and it's kind of nice to know that. But thank you for your question.
I'll shoot my own horn a little bit. Yeah, you said there's not a parallel version of Replicate. I have written a package called Harvester that does do parallel replications and parallel simulations and collecting results and all of that. If anyone's interested, I could present on it, or you can just, it's pretty self-explanatory.
Right. I meant to mention that, yes. Using just parallel, it's not Replicate, but yeah, Harvester has some nice functions for making it a little bit easier to distribute your code out, run all your simulations, bring it all back together. I didn't realize you had an actual Replicate.
It's not called Replicate.
Okay, but it's
called Farm.
It's the same idea, yeah.
Yeah, it's all farming funds in the package. So it's farming, gathering, seeding, and harvesting. So
yeah, so there are other tools beyond just these, but I was keeping it mostly to what comes with R. But Harvester is great for those things.
Just more on the sort of after effects when you're presenting this to the people you're working with. I found sometimes when I'm doing simulations, clients don't want to trust it. They're sort of like, oh, so the computer just simulated this, and so have you gotten any pushback? Are they okay with these models?
Sometimes I don't tell them that I did simulations. I said, here's the results of the power study. You know, and you know, it depends. Like some people, you know, if I say anything more than that, their eyes are going to glaze over and it's all black box to them anyway. So that type of guy is like, here's the results of the power study. Those are a little bit more sophisticated. You know, if they're a little bit wary of simulations, I'll actually start off with the first case where I say, here is the algebraic mathematical code. Here's my simulation. Look how well they match. Now, our situation is more complicated, where this one falls down and doesn't work, and you either need to send me to get a PhD in math and wait, you know, another 4 to 6 years for that to happen, and fund that whole thing, or we can do the simulations that we know agreed here, and I can do it in 10 minutes. And when I explain it like that, a lot of them are a lot more happy to trust the simulations. When I show that they agree here, and then, you know, and well, there's no guarantee that even with a PhD in math, I'll still be able to answer this one this way, but I can look at it. And I actually find a lot of the people that I show the simulations to, I can show them the actual, you know, a few of the samples. I don't show them all million, but I show a couple of the samples, and they can look at it and say, it's like, yeah, that's what I think the data is going to look like. And I say, okay, if you do this a whole bunch of times, this is what's going to come out. And you can see it's like, okay, you know, the computer is doing this, but in real life, you know, sometimes you'll be down here and sometimes you'll be up here. And most of the people I work with who are willing to take the time to think about it actually appreciate the simulations. Maybe I'm lucky in who I work with, but you know, most of them end up trusting me that if I trust the computer, you know, there must be something reasonable in there. I think I told one person that, you know, if you really wanted to argue with me, that come talk to me after he finished his PhD in statistics. And the other guy in the group said, "No, we'll go with your stuff." He didn't want to wait that long. I try not to say those things out loud too often, but okay, you know, like most of the people I work with are pretty good, but occasionally you get somebody that has an MD after their name and they think that's, you know, I'm not a real doctor because it's just a PhD. But if you throw out the right terms in that, they sort of is like, okay, maybe he did learn something in his graduate study, even if he can't prescribe medicine.
Let's thank Greg again. Oh, the package, there are a couple comments coming in. The package SKPR provides a framework to do these exact parallel calculations, these exact parallel power calculations in parallel with external libraries. So,
yeah, there are other packages out that'll make some of these things easier and simpler. And I find, you know, the simple cases, it's run it, you know, if it runs in 20 seconds, I'm not going to bother to parallelize it. Some of these things, a single run takes a minute. And so that, you know, to get up to 100 even, parallelizing can cut that time in a third or something. It's going to be worth it there. But you know, I'll usually start off with a small one, see how long that takes, and say, is this worth my effort to parallelize it? But, and if it's going to take really long, it is really good to go out and find some of these other packages to help.
So,